that's the agenda with which I'm going to talk about the time frequency analysis or present this talk. It's the title reads linear time series analysis, but anything can be brought under that umbrella, and this does belong to that umbrella. The only extension is we are not looking at just linear time invariant systems any longer. We are looking at linear time varying, or you can say non-stationary system. Okay. So let me just quickly go through the agenda here and give you some motivation behind the topic today. Not necessarily again with respect to any thermoacoustic application, but I'm sure you would appreciate it even if it isn't. And then talk about how briefly the historical developments, present to you the concepts of spectrogram and Wigner-Villey distributions, on the way to talk about wavelengths. It's more of a technical story that I'm going to present, not a very detailed lecture. Then talk about a couple of applications, converge with some concluding remarks. And when you have questions at the end of the talk, I'll be able to answer if you have application-oriented questions. You can describe your problem and I may be able to answer. Okay, so the framework within which this talk is being presented is the multi-scale system framework. And I know that thermoacoustic systems do fall in this category. I don't have to really describe what a multi-scale system is in detail, but just to refresh, it's a system where you have phenomena happening at different time scales. And the nice physics viewpoint is that you have different frequencies appearing over different time durations. In other words, you may have a sudden burst of high frequency phenomenon or event, and then you have a low frequency dominating for a while and so on. And there are several natural processes that fall into this framework: earthquakes, vibrations, equipment faults, fuel cell systems, and so on. In fact, a classic example that's given is the changing colors of flowers during sunrise and sunset. And because colors are associated with frequencies, you can therefore say it's a nice example of a time frequency system. Okay, so just to give you some pictorial motivation here, I have 4 different synthetic, but not all of them are synthetic. The top 2 are actually real-life examples from industrial processes, and the bottom 2 are synthetic ones. Incidentally, the top 2 are generated using the wavelet analysis, and the bottom 2 are generated using Wigner-Villey distributions. What you're seeing is actually so what you see here is in all these plots, the big ones are all the energy density plots. On the x-axis you have time, on the y-axis you have frequency. So we call this as the energy density plots in the time frequency plane. And these are useful in telling me what frequencies existed in the signal over what durations. Note that I'm not saying at what times, because that's a very difficult question to answer, not necessarily answerable. So here, for example, this is the sea surface temperature from some geographical region, and on the top you see the time series plot, and on the left here, left panel, you see the classical spectral density plot, which tells me what frequencies are present in this series here. And this gives me much more information about the frequency varying, time varying characteristics of the frequency. And as the color bar indicates, the red region corresponds to the most intense activity. So if you want to track, for example, the frequency, the oscillation at this frequency, you can see that it doesn't really persist over all times. And that helps me, I'm not going to go through this example in detail, but that can help me in determining when a particular periodic phenomenon appears and goes. And here, I have an industrial measurement, where until this time there is no oscillatory behavior except for an outlier here, and then I have oscillations in this loop, control loop, and then again it dies down. So that's because maybe the controller is taking some action on reducing this oscillation. If I look at a classic Fourier analysis, again, it tells me only that the spectral, the frequency domain information, but I wouldn't know where these oscillations existed. The scaleogram, as we call it, again generated from wavelets, tells me when, or at least over what period these oscillations existed, persisted, and that also there is an outlier. So these two, and of course these two are examples of going from single scale to multi-scale analysis. In a single scale, you assume that things happen, change only in one dimension, typically frequency or time. And coming to these two synthetic examples, I have a single oscillation here corrected by some abnormal event during the period. A visual inspection would not really help me find out when that event existed. But the Wigner-Willi distribution, as you see here, tells me that this oscillation existed throughout the interval of observation. And somewhere in between, an abnormal event occurred, if you want to call it abnormal. And it shows how long it persisted. But let me point out quickly that none of the tools that you see will be able to exactly point out when this event occurred. There will be some smearing, there will be some ambiguity associated with it. But you can run a geometrical, an algorithm which will help you find the regions more accurately. This is only through visual observation that we can say where this abnormality has occurred. And here, this is a sum of chirps, decreasing frequency, increasing frequency, and again the Wigner-Willi distribution really shows this very nicely. And this is where the most intense activity is occurring in the mean. In all this, what should be appreciated is a visual analysis or even the classical spectral analysis will fail to bring out the time-varying nature of the frequencies. And if this is of use to you, of course, you can continue to listen, but if this is not, then you can take a break and speak. Okay. All right. So we'll look at the next. Oh, right. What does it have? Okay, yeah. So this is a quick historical roundup of the events that led to what you see, what you saw in the previous plots. You know, all of you know about Fourier transforms, which came about in the early 1800s. And then somewhere along the line came the concept of spectral densities, the periodogram, nearly, in fact, about 40 years later by Schuster. And gradually people asked, well, what if these periodicities or the oscillations only existed for a short duration compared to the length of the observation? And that's when a lot of activity came about in analyzing non-stationary signals. And let me also say, when I use the term non-stationary, they have different meanings in, at least definitions in deterministic and stochastic frameworks. All right. But you can show that once again, just as the way the spectral representations unify the concept of stationarity in deterministic and stochastic signals framework, you can also show that there is a unified framework for analyzing non-stationary, deterministic, and stochastic signals. So, then came about the idea of short-time Fourier transforms. It was a natural extension. Gradually, then people asked, well, what is the best way to do the short-time Fourier transform? And they ran into some limitations. I'll just briefly talk about the limitations just for illustration. But in parallel, what came about was a beautiful concept known as the Wigner-Willi distribution, which said that instead of computing the energies, just as the way we compute power spectral densities, by first going through a Fourier transform, or you can say through autocovariance functions, and then computing the energy density, Wigner and Willi independently proposed that we could compute the energy distributions, avoiding or bypassing the signal transform route and directly working with the local autocovariance functions. The classical spectrum works with the global autocovariance function. And that's what led to the Wigner-Willi distribution. That had some marvelous results. There were some fantastic theoretical results that came about. Unfortunately, the Wigner-Willi distribution had a very crucial drawback, apart from all the other attractive properties. And But still the Wigner-Willi distribution and its variants, so people did work on it and came about with a practically implementable WVD. But the use of WVD by far has been only in feature extraction or computing the energy densities in time frequency plane. When it came to filtering applications, which is of great interest in signal processing, communications and so on, the WVD could not play much role because it discards the phase of the signals. You have to keep that in mind because it works with autocovariance functions. And then came about the discovery of wavelets. Now wavelets, of course, is a very beautiful story. The way things came about, how several people from different fields came together, not necessarily in a very planned manner, but fortunately they came together, and that really led to the boom of wavelet transforms. Not that it is a panacea or anything else, but it really addresses a lot of nice situations. Okay, so the three tracks that you find, if you jump into the literature of time frequency analysis, you will see three different tracks at least. One is a signal analysis where you're looking at univariate signals, and you're asking what are the features of the signals. Can I break up the time, signal into different frequency bands and still have one foot in time? And the second track is energy localization, as I showed you. Eventually, you will see that most of the applications are in energy, an equal number of applications as in signal analysis, you'll find energy localization. Basically, what I mean by energy localization is computation of energy density for whatever purpose. It could be for feature extraction, it could be for any other application. That's where the Wigner-Willi distribution belongs to. And the third is in modeling, where you're now talking of characterizing the system using time varying frequency response functions and so on. Then there are other applications, of course. Okay, so let me move on. I'll skip this slide. It simply shows you the breadth of the applications of time frequency analysis tools, and you can see that there are not many areas that have been excluded. Anyway, since you will get a copy of this slide, you'll have more time to pick any of these application areas and go into it. Okay, so I'll skip this wavelet slide and come back later on, but let me start off with Fourier transforms because that is at the root of all the time frequency analysis tools. I'm not going to go through the theory and so on. This slide essentially summarizes the entire gamut of Fourier transforms that you have. It has three columns, as you can see. The first column lists the four different types of Fourier transforms, and the second column lists the mathematical definitions for the synthesis as well as analysis of the signal. And the third is the interesting one, which shows the energy density or the spectral power density computation as the case applies. What is to be remembered is the mother of all these three is the Fourier series. That's where the story began, and then gradually it will be extended into other situations. So this situation is for the continuous time periodic case. This is for the continuous time aperiodic case, and these two are the discrete time counterparts of the first one. And of course, the conditions under which these series exist do differ. But what I would like to point out is, which goes unnoticed in many textbooks, is although all these transforms begin with signal analysis, eventually what is of interest is how the energy, what the energy of the signal is made up of, whether you say energy or power. I use the term energy right now, but you can read it as power as well. So in an attempt to break up the signal into its oscillatory constituents, we are essentially asking how the energy is made up of in terms of this energy of this so-called atoms, whether it's sinusoidal atoms or some other atoms. So this by far finds the most number of applications, not this, but this is more at the backbone, I would say, more acts as backbone of the energy analysis. This is what we call as a spectral analysis, which all come about from Parsons relation. Practically, you would implement none of this directly. You would implement Fourier transforms to the DFT, which is what is actually the way to compute is through the fast Fourier transform. That's only an algorithm. It's not a separate transform. Okay. So quickly pointing out the limitations of Fourier analysis for time varying systems or signals. So I have two signals here. You can see the frequencies are simply reversed, otherwise there's not much difference between these two. But if you look at the spectrum, practically they look similar. You can argue that I have not shown the phase information. But when you sit down to compute the phase, for academic signals, typically the faculty are very good at presenting signals that are free of noise in the classroom and then give the noisy data in the assignments. So that's what I'm doing right now, but I've added a slight amount of noise, and that's why you see the small ripples here. Maybe you will notice it. So why am I not showing the phase? When you have noise corrupting the signals, then there is an issue of phase computation. The phase computation simply goes erratic, and it becomes very difficult to detect this transition times from this frequency to this frequency or even here. So practically the phase is only useful in classrooms to talk about how it can be used to detect changes in phenomena. There are a few applications that talk about it. By far, the spectral density problems are useful, and they fail to detect these transitions. The second example here is both are sinusoids, but the only difference is I have an outlier in one of them. I'm sure visually you can detect. Again, when you have noise, you wouldn't be able to detect that. So the spectral densities would look alike, and this could correspond to some situation in your thermoacoustic applications where you have a sudden outburst and then it vanishes. With the spectral density, it will be very difficult to detect. I think the reason is obvious. The basis functions essentially are spread all over time, and they do not capture the time local behavior. That's the main root cause. Always a question is asked, what kind of transform is suited for an application? The answer is very simple. Like basis, like information. Like father, like son, or like mother, like son, whatever it is. But the information that you seek will govern the basis function that you choose. Obviously, when you want to know the time local behavior, in addition to the frequency localization, then Fourier basis is not good. Okay. So then came the idea of short-time Fourier transform. Naturally, you slice the signal into smaller segments and then compute the Fourier transform. This is only for the mathematics is only to give you information that you can digest offline. I'm not going to go over this, but a quick look at these expressions will tell you that essentially we are slicing and then computing the Fourier transform. Or the alternative way of looking at it is I'm taking a Fourier transform with clipped sinusoids, whichever way you look at it. Essentially, I'm modifying the basis functions, and that offers a better perspective. And then once again, you can come up with all the definitions of your energy as in classical spectral analysis and so on, and that you can perfectly reconstruct the signal. This is a discrete time version. This is a continuous time definition of the short-time Fourier transform. So let me show you pictorially. Helps a lot in understanding. So I have again the same sinusoids that I showed you earlier. What I'm showing you here is the spectrogram computed to the short-time Fourier transform. In fact, sorry, not the same signals. It is a signal with an outlier, but located at two different points. And what matters in short-time Fourier transform is how you slice the signal. If you're going to use a window, that is the technical term that's used, if you're going to use a very wide window, then you'll of course get back to classical analysis. If you use a narrow window, then you will be able to detect extremely time localized behavior. But then remember, the resolvability in Fourier analysis depends on how many observations you have in your window. So the frequency resolvability goes down, and that's what exactly you see here. What I'm showing you here is the short-time Fourier analysis with two different window sizes. In the first case, I've used a wide window, and therefore the energy localization and frequency is very nice because the resolvability is very good in frequency. Although this is not as good as you see in the classical analysis, and that's the trade-off that you have. So imagine that this is a time and this is a frequency dimension. So if you look straight here, the time domain signal, you get this, and frequency, you look at it this way. What you're doing in time frequency analysis, choosing a certain angle and trying to see what's best. That's exactly what's happening here. We've completely disregarded the time evolution in classical Fourier analysis. And here we want both feet in both domains, and that's a trade-off. Some smearing of the energy. As you choose a narrower window, yes, the outlier present here is detected much more nicely, but then there is a huge smearing of the energy in the frequency. So that's a classical trade-off, and one can conduct a full semester or 2 semester courses on these concepts. There is a very nice result in signal processing known as the duration bandwidth principle, which is unfortunately known as the uncertainty principle for signals. Because several people try to draw analogies of this duration bandwidth principle with the Heisenberg's uncertainty principle, and the situations are totally different. They look very similar. Okay. So Heisenberg would be disappointed, extremely disappointed. Right. So the basic principle is that if you try to localize the energy, which is characterized in time, which is characterized by what is known as duration, very nicely, or if a signal has very finite duration, small duration in time, then its bandwidth, which corresponds to the spread of energy in frequency, is going to be wide. So the product of duration and bandwidth has a lower bound, and you can derive that lower bound. A good book to read is The Time Frequency Analysis by Leon Cohen, which I'll give you at the end of the talk. Okay. Alright, so we'll assume that short-term Fourier transform is not that great. Unless you know what events you're looking for, then it's very good. Please remember that I'm not advocating any of these tools for your application. It completely depends on your application. In fact, I can show you an example where the much hyped up Regular transforms miserably fails and the Wigner-Rayleigh distribution really performs an excellent job. So, on that note, now here is Wigner-Rayleigh distribution. You can see that there is no signal transform involved here. Particularly, you should look at the definition carefully here. What we are doing in this is we are actually computing a local autocovariance function. The star indicates the complex conjugate. We are computing the Fourier transform of the local autocovariance function. And that, as a natural extension of Wiener-Khinchin theorem, should give you the local energy density. Since they independently came up with this, but you can see there was a gap of at least 15 years. About 15 years. Okay, so this is a very beautiful way of computing the energy density. Why I say beautiful is you can show theoretically that the duration bandwidth principle, the lower bound on that, does not apply to the Wigner-Rayleigh distribution. Which means you can really resolve the time and frequency energy localizations very nicely. You can show that. But, and in addition to many other properties, it's very good. But the major drawback of the Wigner-Rayleigh distribution is it's not guaranteed to be positive value. And that's a big bummer because you want the energy densities to be positive value for them to be meaningful. Okay. And then came the beautiful result in time frequency analysis by Wigner, who showed that there exists no positive valued function which can act as an energy density and which does not violate which does not violate the duration bandwidth principle. The moment you want a positive valued energy density, you will come back to the framework of the duration bandwidth, and there is some trade-off involved. So that's a very classic result established long ago. Yeah.
Big question, what are the limits of time integration?
Well, theoretically, minus infinity to infinity. But then you have, as in Fourier analysis, you first derive the, the discrete time version and then the finite sample version.
But then I don't understand why this is local in time, it's just shifted in time.
Sorry? No,
we have the correlation here, and you shift the reference point, so to speak, but the tau ranges from minus to plus.
Oh, I'm sorry. No. The time limits are not minus infinity to infinity. Sorry. The tau, which is your center point, you can go from anywhere, from the beginning to the end of the signal. Alright? So, what happens is you're standing this time t, I think the notation is a confusion here. You're standing at time t and you're looking to the left by tau by 2 and to the right by tau by 2. Okay? And then you're computing many such here. Many such shifts. That's why the integrand is tau, not the t. T here refers to the time at which you're standing and analyzing the signal. So what you're doing is you take a small slice of signal to your left and right of width tau by 2, compute the Fourier transform, and then you keep increasing your tau. So that way you're capturing the local properties of the signal for different values of tau. So that's just a matter of notation, I guess. Does it answer your question?
No, but even then, what is the limit actually? That is what I think it might.
For which limit? Limit for what?
Tau is which you are integrating.
Right, right.
What is the limits on tau? Minus infinity to infinity?
Yes, of course. From the beginning, but if you, I mean, this is the theoretical definition. It's just like in the classical Fourier definition, the limits run from minus infinity to infinity. But when you start writing the discrete time versions and the sample versions, then obviously, let us say autocovariance function, right?
Yeah. So
It's the same story. I can compute autocovariance functions at any lag L. But when I have a signal of finite length n observations, the lags up to which I can compute is n minus 1, minus modulus of n minus 1. So, in a practical analysis, your tau would run from minus n minus 1 to plus n minus 1. Because that is how far you can compute the autocovariance function. That's all. Okay. So, just to show you, there was another drawback to the Wigner-Willi distribution, and I'm just illustrating this pictorially. So this is the signal that you've seen earlier, and you should. This is a Wigner-Willi distribution, the energy computation, time frequency. You can see that it is showing energy in this duration within this very fine band, and again for this region. But then there is a third one that's coming in between these two, and that's the problem with the original Wigner-Willi distribution, which we call as the interference term. Okay. And this interference term can be theoretically shown. You can exactly determine where this interference term occurs in the time frequency plane. It exactly occurs geometrically midway. Okay. So you can then perform some modifications of this Wigner-Willi distribution, which people did, and came up with the so-called pseudo-smooth Wigner-Willi distribution, where you get rid of the interference term, and this is what you end up with. Observe that the sacrifice that you have made is on the frequency localization of the energy. So there is more smearing of the energy here in the frequency than here, and whereas the time is not, the sacrifice that you make on the time localization is not so much. But if you were to take the scaleogram, that is through wavelet analysis, if you were to compute that for this signal, it would fare poorly compared to this. And the reason will become obvious once I tell you what wavelets do. Okay.
So in the smooth version, there is some decaying kernel that you use in your integral?
Actually, the theory for the smooth Wigner-Willi distribution, yes, you're right, you do use a kernel, and that's what Cohen's contribution was. If you go into the time frequency literature, Cohen's class of generalized functions can do accommodate this Wigner-Willi, smooth Wigner-Willi distribution. So you're right, so you do use the smoothing kernel. But initially that was not the framework within which this was done. It's Cohen who actually came up with the unified framework. Initially what was done is this interference term was, this entire thing was transformed into a different plane, and there is something called ambiguity function which helps you resolve ambiguity when you come back. But it's a very good question. So later on, Cohen actually unified all of this into kernel based. And you can show that scaleogram that you get from wavelets, spectrogram that you get from shorthand Fourier transform, all of that actually fall into the framework. In fact, you can start from Wigner-Willi distribution here and then apply suitable kernels, and you end up with wavelet-based scalograms, or you can end up with spectrograms. So that's why you see in literature many authors claiming that this is better. This is better because it offers a better framework and it accommodates the other and so on. But nobody wins the argument. Okay. So this is the third in the list that I wanted to talk about, the continuous wavelet transform. And once again here you can see a transform, but the main difference between the earlier two and this one is now we have a concept called scale, which for quick understanding, so yes, there is a theoretical basis to what I am saying, that it represents the inverse of frequency. And to give you an example by analogy, when you're looking at maps, and you know that maps are drawn to a certain scale. So when these maps are drawn to a certain scale, my question to you is, when maps are drawn to high scale, do you see more points on a map or less points on a map? When you see a map in it, it's drawn to very high scales. Do you see more points on a map or fewer points on a map? Sorry? You're confident? You have company?
No, I was just going to ask a question. You
Yes.
said high.
Right.
What do you mean?
Oh, well, high scale is typically understood as,
High frequency scale?
no, so geographically, spatially. So you say 1 centimeter on a map represents 1,000 kilometers. Right, that's what is drawn, map drawn to. Typically, it's a very coarse scale. So, yeah, so that's probably a better technical term, and that's a term that's used also in wavelength analysis or time frequency analysis. So when you see maps drawn to a very coarse scale, which corresponds to high scale parameter S value here, you see fewer details, which means you end up with very coarse approximations. And approximations by nature are low frequency components. They do not contain the high frequency or the details part of it. So that's why high scale corresponds to low frequency. In other words, if I compute a wavelet transform with high values of S, then what you're doing is you're essentially looking at the low frequency component of the signal. You're trying to capture that. And if you're looking at low values of S, then you're trying to capture the high frequency component. And I apologize for the notation confusion here. Earlier I used T and tau, and now I interchange the tau and T. Really sorry for that. Okay. Right, so it is a transform after all, and it helps a lot when you look at any transform as projection onto some basis functions. Fourier analysis involves projections onto sinusoidal basis. Short-term Fourier transform involves projection of the same signal onto clipped sinusoids. Wigner-Willi distribution, when they came up, they said no, there is no signal analysis, there is no signal transform that's involved. But then you could easily go back and say, look at the expression. You can say, who said it is not a transform? Right? All you have to do is you rewrite this again. You can disregard, you can take this as a signal, or you can even do a change of indices, and then take the rest of it as a basis. The only difference between the Fourier basis and the basis in WAD is that the basis is time varying. That's all. There is also a sinusoid involved. It is some modification of frequency omega. So, even Wigner-Willi distributions can be thought of as a signal transform in a basis space, and so is wavelets. The only difference is in the basis. And the second point here is the basis function in wavelets are localized in time and frequency. So to actually help you understand this, let me take you to this and come back. Okay. So what I'm showing you here is in the center what is known as a mother wavelet. You need a reference for the scale. What you mean by the reference scale, which is S equals 1, that's typically considered as a reference scale. And the wavelet, in other words, this is the basic basis function. It is untouched. It is a pristine one. What you see here is the Fourier transform of this basis function. Actually, the basis function is complex value. I'm only showing you the real part of it. So the Fourier transform of the complex value is a real one. You can see that the Fourier transform of it has a certain finite bandwidth. And from a signal processing viewpoint, we say that this basis function acts like a high pass filter or band pass filter. So, with this center frequency. Now, what happens when you scale? When you choose high values of S, what you're essentially doing is you're dilating the mother wave. And in frequency domain, or from a filtering viewpoint, essentially what's happening is the center frequency shifts. In other words, the band pass, now the band has shifted to lower frequencies. But you should also observe that the bandwidth has shrunk. And this is again this is conforming to the duration bandwidth principle. Here now the signal duration has increased, but then the bandwidth has come down. So dilated wavelets or highly wavelets with high scale allow you to capture the low frequency behavior. The simple understanding of wavelet transform comes about from signal processing perspective. When you compute the wavelet transform of a signal, essentially you are filtering. When you compute the wavelet transform of a signal with this dilated wavelet, you would be extracting the low frequency component, but with very nice localization of the energy in frequency. Now, observe that the basis function has started to expand its duration. Therefore, it will not be able to capture any time localization, not be able to give you good time localization of that low frequency component. That is the trade-off that you make in wavelengths. All right. And going here, in fact, it should have been this way. The reason I drew this way is because in terms of frequency, this is high. This is the base frequency, which we call as the central frequency, and this is the low frequency. In terms of scale, the order is reversed. So now I have compressed this wavelet. The filtering, if you look at from a filtering viewpoint, the band has shifted, and the center has moved to the right, which means now you are traversing the high frequency regime. But then what is the trade-off? You lose the energy localization in frequency. Since the basis function is more compressed or has a shorter duration, you will be able to capture good time localization property. So that's the trade-off in wavelet analysis. As you move up the frequency scale, you will get very good energy localization in time, but you lose the localization in frequency. Okay. This is a basic continuous wavelet transform. It is not necessarily continuous time wavelet transform. We can actually compute CWT even for sample data. Okay, so what about other types of wavelets? There are plenty. I'm only showing you 6 different types here. You can see that each of this basis function, first of all, has a compact support in time. That's a technical term. Basically, it says it's short-lived. Most of them have perfect compact support, which means they die down exactly in finite time. But there is at least one wavelet which does not die down mathematically, it dies down actually exponentially in time. And you can figure out which one of this is that. I leave that as a simple exercise. But what I want to point out here is the other feature, which is that this is the original wavelet historically by R in early 1900s. It has a discontinuity, simple boxcar-like function. So this wavelet is very well suited for detecting discontinuities. If you're detecting discontinuities, because it has the feature in it. Now, there are, and as you move to other wavelets, obviously they are smoother. So there are different characteristics of these basis functions, wavelet basis functions, that will help you decide what wavelet to choose. So there are different wavelets, and you can find that there are bi-orthogonal wavelets, non-orthogonal wavelets, and so on, and weird wavelets. If you look at it from a basis function viewpoint, then these are all very easy to understand. But I'm not going to go over this. As I said, there are 3 key properties in choosing the wavelet basis. One is the compact support of the mother wave, and then the vanishing moments, which essentially determines to what degree you can detect the discontinuity. In other words, whether you can detect discontinuity in the signal, or its derivative, or its second derivative, and so on. It's a measure of the regularity also of the signal. And then the symmetry property helps you in phase, particularly for complex wavelets and so on, detecting the phase variations. Okay. So this is a very, very, very short summary of what wavelet transforms are. But let me tell you very quickly, when you jump into wavelet literature, if you're a beginner, you will be bombarded with at least a few hundreds of books and articles. And the likelihood that you will pick up the article or the book that can actually repel you like anything is very high. Okay, that's the reason is there are 3 domains in which wavelets have actually evolved. One is physics, where people looked upon wavelets as solutions to time frequency analysis. And then there is signal processing, where engineers try to develop multi-rate bandpass filters. And then there are mathematicians who wanted multi-resolution approximations to wavelets. So they looked upon wavelets as basis functions. As an engineer, I don't claim to be an engineer, but at least coming from an engineering background, when I started studying wavelets, the first book, unfortunately, I picked up was a mathematics book, and I closed it immediately. Right? Because the first page contained all the symbols that you typically find in engineering text. So I'm not saying that mathematicians don't write books very well. I'm not saying that. But if you're an engineer, it's best that you seek a tutorial written by an engineer. It's a lot more easier, and that's how I learned as well. Okay. Right. So let me move on quickly and then talk about scaleograph, which is essentially computed through the wavelet transform this way. So you compute the wavelet transform, and then from there you compute the scaleograph as a modular square. Clearly, this assumes that you are using a complex wavelet transform. Otherwise, there is no need to assume that the wavelet transform is complex. And that's typically the case. When you are computing the CWT, the continuous wavelet transform, typically you would use a complex wavelet because you would also want to capture the phase varying characteristics of the signal. And there is some normalization that is required, and I'm not going to go into the details, but this normalization is keeping in mind the differences in widths of the wavelets at different scales. Beyond that, I'm not going to dwell on this. So just as an example here, I show you an example that you've seen already. The difference between this analysis, scaleogram analysis, and the short-time Fourier transform analysis is, I have a lot of bookkeeping to do in short-time Fourier transform. I have to try out different window widths for capturing different features, right? Whereas here, I don't have to do that. The wavelet transform is suited naturally to capture high frequency variations that exist over very short intervals of time and low frequencies over long durations. That's why all I have to do is compute the scaleogram, and it is showing me the characteristics, time frequency characteristics of the signal. If the situation was the other way around, suppose you had a high frequency component with a very low frequency component that existed for a short period, then wavelets wouldn't be the right tool for you. Okay, so that's where you run into the limitations of wavelets. So let's look at the second example here. You can see what's happening here. There are three different frequencies: amplitude modulation, a Gaussian modulated amplitude modulated wave. Look at how poor the wavelet is in terms of time localization. If I were to show you the Viterbi distribution for this, it would be so beautiful. You would actually capture the time frequency localization very nicely. Right? Here, what is the problem I have? Well, this is a high frequency. Among the three, this is the highest. And it is showing me that it existed during this time fairly well. But this is the lowest, and that's where I have difficulty with the time localization. The frequency localization of energy is very nice, but obviously it has not done a good job. And then you have the third, which is a medium frequency in this signal. It's a compromise. So this is also illustrating how good wavelets are, and also illustrating the limitations of wavelets. All these plots are generated through two different packages. One is the WaveLab package that's based in MATLAB, and then there is a WTC package by Grinstead and others, again on MATLAB based platform. So this is from, and by the way, this plot is coming from the time frequency toolbox. So that's the third toolbox, time frequency toolbox. That's written by the pioneers in this area. I think the development is strong. Yes.
The previous chart.
Right. The previous slide. Talk, I wouldn't know. Right.
The previous slide. I could understand what is the limitation I couldn't.
Limitation, okay. So limitation is that if I want to know when this low frequency component existed from this energy density plot, then it gives me an incorrect picture. At least visually it gives me an incorrect picture. But if you see the intensity here, most intense activity is almost kind of corresponding to the duration of the signal. So this is where you have to be careful when you analyze any signal with any transform. Always the features that you see in the transform domain will contain both the signal features and the artifacts introduced by the transform. So these side things that you see here, like the Saturn rings, they are the artifacts of the transform. So you should not mistake this for the signal features. And most of the times you wouldn't know. Does it answer your question? Yes.
Does these blocks correspond to the particular scale of the mother wavelength?
Yeah.
So if you choose a different scale, you will see.
The situation is going to be the same. Typically, you don't, although I described the wavelets with respect to scale, the characterizing frequency is with what is known as a center frequency of the mother wave. You can choose different center frequencies, absolutely not a problem. You're right, it's a very good point. You can choose a center frequency according to your application, but you wouldn't know it has to be iterated. Right? If you, for a situation like this, choosing the center frequency wouldn't help much. Okay? Because whatever center frequency you choose for the mother wave, there is some compromise that you make as you move to high frequencies and low frequencies. Alright? So, choosing the center frequency would result in a different compromise, that's all. But this compromise won't vanish. Basically, you may improve the time localization here. Alright? But then you will lose out on the energy localization. Because all of these transforms are bound by the duration bandwidth principle. Okay. So if you try to localize the energy in time, even for the parts of the signal, the original duration bandwidth principle is for the entire signal. Here you are looking at parts of the signal. There is a duration bandwidth principle, local version of the duration bandwidth principle, but the connotation is the same. Again, your ability to resolve finely the energy in time and frequency is not arbitrary. You don't have that freedom in both domains. But it's a good point. Essentially, it will result in a different problem.
So in that sense, could we say that you've chosen the center frequency to be the highest frequency for this particular block?
No, I have chosen a center frequency to be 1 in this. I mean, that is how this toolbox computes it. I didn't choose it. The reason is more of a convenience of understanding. Because when you choose, I have generated with this Morlet wavelet, which is characterized by a center frequency omega naught, and I have chosen that to be in such a way, not really 1, but I have chosen to be 6 point something, which will give me a perfect inverse relation between scale and frequency. So you can show that when you choose omega c to be about 6 point something, in a detailed workshop that I conducted that has all the details. Then you can show that, sorry, S is 1 over F. Alright, I'm only going to talk a minute on this DWT and then move on, because if I get into DWT, which is where a lot of applications are, in fact, in signal compression and estimation and so on, yet I don't want to get into it. That's probably the reason also I don't want to get into it. People, there's a lot of misconceptions. I think that DWT is another transform. Just like in the Fourier case, the original transform is the Fourier series from where the rest originated. Here it's even more significant. The DWT in fact comes about from CWT when you evaluate it at specific scales and translations. See, when you are performing a transform, such as a wavelet transform, with any transform, what you do is you bring your basis function and you match parts of the signal with this basis function, and wherever the matching is high, the correlation will actually show up very high. That's why it's useful to view all these transforms as correlations. So when you look at wavelet transform, you're bringing your mother wave or compressed or dilated wave, placing it at the beginning of the signal, and then traversing it along the length of the signal. Now, how you traverse is your choice. Whether you're going to march ahead in time in one sample or proportional to the width of the wavelet is your choice, but it does make a difference in the representation. If you're going to march every sample, then what you will end up with is what is known as a redundant representation, because you would have captured that information already. So what discrete wavelet transform does is it actually asks you to march proportional to the width of the wavelet, so that you end up with minimal representation. And that has got to do with the fact that you are analyzing a one-dimensional signal, assuming that you are looking at univariate signals, and you are giving it a 2D representation. So obviously your 2D representation, if you don't take enough precaution, you will end up with a redundant representation. Now there's no harm in that. But if you're thinking of compact representation, compression, and so on, that you find in images, then that's not the best way. DWT is a highly redundant representation, where there is no restriction on how you march ahead in your time and scale. DWT says you march ahead in time and in the scale. So you only evaluate at specific points, then you end up with a very compact representation, and essentially what you end up with is a family of orthogonal basis functions. And that's exactly what you see in this expression here. I'm evaluating at a specific scales and specific translations, and the translations are proportional to the scale at which you're looking at. Okay, so I leave the DWT part. And what I'll do is I'll speak this. If I have time, I'll come back, because I want to go to the, I'll come back to the estimation. I just want to talk two applications very quickly in the interest of time. The first is what we do in control loop, in process control. And I know that thermoacoustic systems, a lot of them are naturally feedback systems. And whether this case applies to you or not, I leave it to you to find that. So here is a classic feedback system, and in control literature, a lot of time has been spent on design of controllers. But of late, over the last 2 decades, we have been asking the question, how well these controllers are doing. It's like going to a doctor and asking, how am I doing? Because my human body is equipped with plenty of control loops doing their jobs. And when you go for a health monitoring, essentially that's what you're asking, whether my sugar is in its control, is controlled well, or the hormonal levels or whatever, everything is being controlled well. That's exactly what you're doing here in control loop performance monitoring, where you're asking whether the controller is doing its job. Now, when the controller fails to do what it is supposed to be doing, there are a number of symptoms that can arise, just like a human body. One of the key symptoms that you will see is oscillations in the plant. And that's not only because the controller is doing a poor job. Maybe there is a valve, there is an actuator nonlinearity, or there is an external oscillatory wave, and so on. So whatever may be the cause, oscillations are a common symptom. And the idea in using wavelet analysis here, initially you use spectral analysis, but then the use of wavelets brings about a nice perspective here, or gives more insights, I would say. So here I have, from an industrial, from a refinery, I have the measurements from the control loops. And what you see here is a scaleogram. The cone of influence is this cone. So whatever falls within this region can be considered as statistically significant. And whatever falls outside this cone is your own personal influence. Okay. You can't really claim it as something very scientific. Okay. So the difference between the behavior of these two tags, both contain similar oscillations, as pointed out by the spectral densities. But here you can get more insights. You can see that the control, the oscillation is not persistent. Alright. You can see that it appears and goes away, and particularly there is nothing happening in the initial period. And this tells me a lot more about the control loop, and also points out to what could be the source. If these were the only two loops that are oscillating, one would say that this is the one that this is the cause, because naturally you cannot have this as a cause. This could be more as an effect, and there could be probably a delay or something would have happened that caused the oscillations to set in at a later time. So just a very small glimpse of the application, the number of applications. I'll give you a reference. There is a review article that we wrote up recently in Advances in Chem Cleansing, but it has got necessarily nothing to do with chem cleansing alone. It's applications of modeling wavelets and estimation, control, and modeling. So that brings me to the final thing that I want to talk about, which is what I set out at the beginning of this talk. Extension of the classical FRFs that you deal with in thermoacoustics to the time frequency domain. Just as we have frequency response functions in classical LTI domain, you can define a time frequency response in the wavelet domain, and the expression looks very similar. Except that now this time frequency response will give you the time varying characteristics of the frequency response function. And that's very useful in modeling time varying systems, linear time varying systems. And there are quite a few applications of this in non-aerospace, non-chemical engineering and non-thermoacoustics. There are mechanical engineering applications, a few aerospace applications. And as an extension of this, now you can define cross wavelet transform, which is an analog of the cross spectral density. And as an analog of coherence, you can also define wavelet coherence, which does the same job as the coherence. You know that coherence is a measure of linearity in frequency domain. Wherever the coherence is high, in whichever frequency region, you can expect linearity, linear relationship in that range. And now you extend this to the time frequency plane. And there are a number of applications of this as well, and I've given you the references. In analyzing atmospheric processes, even engineering systems and so on, the basic assumption is that the linear time varying system is locally in the time frequency plane LTI. That is the assumption that you make, whether it is stated explicitly or not. This expression that you see is simply telling you that practically you will have to use a smooth version of this wavelet transform in computing the wavelet coherence. I'm not showing you any applications per se because we have applied this in control loop performance. For example, we have applied the cross wavelet transform. But describing the application will definitely take some more time. So I had to choose between going through, giving you an overview of the theory or going through the application detail, and chose the former. So hopefully it's not a disappointment for you. And there are a number of other things, other applications and so on. So this is the primary reference that from where most of the material today is taken. This actually gives you, the first half of this gives you a tutorial overview of an expanded version of what I went through today, theoretically. And then the rest of the paper talks about applications in signal estimation and so on. There is one of the most key applications of wavelet transforms is in signal estimation, or what is known as denoising. And what I skipped was a signal estimation, classical way of estimating with wavelets, and a more modern way of estimating with wavelets known as consistent estimation and so on. Both of which are described in this paper. It will take me another 10 to 15 minutes at least to describe that, but I don't want to do that in the interest of time. So with this, I stop and take a few questions if you have. Thank you.
I'm afraid we have to skip the questions session because we are running short of time. But we can have the questions over an informal session because we are breaking for tea now. And we can thank Professor Kandila.